Hi, I'm Ethan Fish. This is my challenge assessment 3, the conduction temperature profile project. First, we'll start out with the scenario or the problem here. So you have a long homogeneous resistance wire of radius R naught equals 0.3 centimeters and thermal conductivity of 15.2 watts per meter Kelvin. It's being used to boil water at atmospheric pressure by the passage of electric current. So heat is generated in the wire uniformly as a result of resistance heating at a rate of 16.4. Heat generated is transferred to water at 100 degrees Celsius by convection with an average heat transfer coefficient of 320 or 3200, sorry. In addition to this project's expectations, we also want to consider the temperature at the center line of the wire to help with the second goal. So our goals here, we want to justify and simplify the heat conduction equation, identify all boundary conditions, the equation for the temperature distribution, graph the temperature distributions, and analyze and adjust three parameters to see their effects on the system. And finally, we will redesign to improve this scenario. Okay, so here we go into our equations and some of our calculations. So assumptions are the heat transfer is steady state. It's one-dimensional heat transfer. Thermal conductivity is constant, and our heat generation is uniform. So as you can see here on the bottom left-hand corner, we have the full heat conduction equation, which gets simplified into the heat conduction equation for this specific scenario. As you can see, it getting worked out right here. Then we go up here to the top right. We're going to apply our boundary conditions. So we have R equals 0, which is the center line. So you can see that get worked out to apply the boundary condition of, and you get T of R is negative Q dot over 4K times R squared plus C2. We go down here to our second boundary condition, which is R equals R naught, is the outer wire radius. And you can see that getting worked out here to apply that boundary condition. And then we go down here to find the temperature at the center line. We take T of 0 equals T infinity over Q dot over 4K times the radius squared plus Q dot radius over 2H. We plug those numbers in and we get this 125 degrees Celsius at the center line. Here we have the temperature distribution, exponential growth as the radius increases. As you can see here on the right hand side in this graph, you can see it gradually growing exponentially as the radius gets larger. So now we want to modify our T infinity. As you can see on the right hand side in the table in the graph here, we lowered it, raised it, and we showed the original. So the raised is the red dots, the lowered is the light green. And you can see the parameters that we used. So in T infinity, which is the surroundings, at 100 degrees Celsius, we increased it to 250 degrees Celsius and decreased to 25 degrees Celsius. We use a constant radius increase, so we can kind of gradually see that as the radius increases. We showed our original temperature at the center line as radius increased, and then we kind of showed here what happens with the increased radius and decreased. So you can see it's a uniform as it grows, but it's still an exponential growth. Here we modified our Q dot. You can see we raised it, which is the blue dots, lowered it was the orange, and the original is the green. So the original Q dot was 16.4. We increased it to 25, and we decreased it to 10. Similar to modifying the Q infinity, we showed the temperature at the center line, and then with the modifications done, increased and decreased. So you can see it changes the growth as the radius increases, so that exponential is higher and lower based on Q dot getting raised or lowered. Then thirdly, we modified the H values. So we lowered it and raised it, similar to the other two. Originally it was 3200. We increased it to 5,000 and decreased it to 2,000. So we also found the temperature at center line based on the increases of H. So, as you can see from the graph here, the lowered H actually increases the temperature, and the increased H decreases the temperature as the radius increases. With this information, we were able to make some improvements to the wire design. So an increase in the radius of the wire will allow for temperature to be substantially higher through the center. Larger heat generation will be beneficial to increase temperature as the radius is larger. And specific material with a smaller thermal conductivity would give a higher resistance to allow for more heat to the water. So your water would boil faster and heat up quicker. And the warmer the air of the surroundings, the more it will heat the wire, which is not always something you can determine. So that's kind of, so if we were in a controlled room, we would be able to understand that better and get a very precise and good heating mechanism with having the air temperature at a certain temperature. So all these components allowed us to make an improvement to our heating system and would allow for a better system. Thank you.